Hi guys, alright, we have chapter 28, number 58 here, in which part A asks us to show that rho naught equals 3q over pi r cubed. In order to do this, the hint in the book says we'll need a volume integral. So in order to do this, for the volume of this sphere integral here, I'm going to take a thin slice of it here, kind of like a Gaussian surface, an enclosed area of this sphere, and take a thin slice of it with a radius r. The question also says we have a linear charge density that decreases as we go out, so we also have that here in this problem. But first I'm going to calculate the change of the volume in this small little shell here, or create a formula for it, I apologize. So it's going to be really our surface, 4 pi r squared, and it's going to depend on what the small radius here is changing, how it's changing. The charge inside of this zone is going to be QE, the charge of the enclosed area, and that's going to equal the integral of dq. In this case, dq is going to be the surface, 4 pi r squared, times the charge density rho with respect to r. And this is going to be on our limits of integration from 0 to r, the center point there all the way out to the edge of our sphere here. So as we move through here, we plug in our rho that the book gave us. Rho is rho naught times the quantity 1 minus little r over big R. Again, this is all in respect to with respect to r. We're going to be able to pull out the constants now, the constants for this integration, and really just get it down to the parts with the r. As we move through simple integration here, 1/3 r cubed minus r to the 4th over 4r, we can plug in the limits of integration 0 to big R. As we plug in, we can solve out and simplify. Ultimately, we're going to simplify down to rho naught equals 3q over pi r cubed. So that basically proves the, there's the simplification there for you guys. Just algebra again through this zone right in there. So that's basically showing us the rho naught for these sphere problems. Now we get us part B. Now part B for these problems, or for problem 58, I apologize, asks to show the electric field inside the sphere that points radially outward with a magnitude that they're calling E equals QR over 4 pi epsilon naught r cubed times the quantity 4 minus 3 little r over big R. So this one we're going to need to use the Gauss's rule, and we have a left-hand side and a right-hand side here, using the same image as the same drawing as from the previous part A. So get familiar with that picture there. So we're going to move on here. We're going to have the left-hand side and the right-hand side. Left-hand side is your typical double integral that's enclosed. It's your enclosed surface with an electric field and surface there. And that's going to equal your right-hand side, your charge of the enclosed surface over some constant epsilon naught. So we'll start here with the left-hand side, real simple. E is going to be constant as we've dealt with spheres enough here, but the normal vector is going to be parallel with the electric field vectors that are coming out of here, and so that allows us to say it's constant and pull it out. The ds is the surface of the sphere here, 4 pi r squared. We should be familiar with that by now. So now we'll move on to the right side. For the QE, the charge of the enclosed area, we're going to have a surface times some charge density. This is going to be the integral of that zone. We're going to integrate from 0 to little r for this case, and we're going to have 4 pi r squared as our surface, times it by, again, from the previous problem, it's given that rho is rho naught times the quantity 1 minus little r over big R with respect to r. Pull out the same constants as previous problem, solve through it the exact same way. But once we get to this point, we're going to plug the left-hand side back in. So now once we plug this left-hand side back in, we're going to have all of this The right-hand side has been algebraically manipulated down much neater. We're going to be able to plug in the 3q over pi r squared that we solved for in the part A. We're going to plug that in for rho naught, which is right here. It moves down to right there. Then we're also going to pull out the 1 over epsilon naught, and from there again it's a lot of algebra, pulling out a 1/3 r over 3, and then we're going to have cancellations. We know that 4 pi is there, 4 pi is there. We're going to have it all canceled out, and we're ultimately going to only be left with your big Q, your little r, over your 4 pi r cubed epsilon naught. And I'll leave the algebra for you guys to do for sake of the video of this time, the time of this video. But you guys can solve through, cancel what you'd like to cancel, and ultimately you're going to be left with this equation here, which matches the book's part B exactly as it needs to. So that shows that the electric field inside the sphere points radially outward with this magnitude here. Lastly, part C, pretty simple. It's just changing part B, the small r radius with the big R, and with that we're just going to see what the expected value when r equals the big R here for this problem. So in order to do that, again we're going to plug in all the big R's in for the little r's at the previous answer for part B, this guy. So that little r there is going to become a big R, and so we'll see what we get here. So we're going to have the same formula right here, except now there's the big R there, not the little r. And simplifying out the canceling r's, we're left with an r squared on the bottom, and we have 1 over 4 pi epsilon naught. Well, that's familiar for us from the book, that we know is k. So this answer is similar to kq over r squared. Now, this tells us that all charge q is inside of r, and this equation, as you may recall, is that of a point charge. So it makes perfect sense for the sphere. That's the best Gaussian surface for us to use around a point charge. And yeah, that's it for number 58 of chapter 28. Thank you.